Okay, so good evening from the UK. It's 7 o'clock where I am. So I'm going to give a nice evening class on sort of Whitham modulation theory for multiple symmetries and how these will lead to nonlinear equations. So this is some joint work that I've been doing with Tom to generalize the single phase stuff we've done in the past. So I'll start off with a bit of a review on that. So using the modulation theory for single phase, we'd end up with a KdV whose coefficients were directly related to the derivatives of the conservation laws. So the conservation law components are A and B in this nice squiggly writing. And so these two have a generic form with derivatives with respect to their wave parameters, wave number k, frequency omega. And these are usually polynomials, really nice and easy to work out, depending on the symmetry you're considering. The only one not related to conservation laws is this coefficient of dispersion k. Now, that one's quite easy to work out as well. That's related to just a sort of linear analysis of the linear operator. And so you can do the calculation of this and these all in advance to work out the coefficients of the KdV. Okay? Now, what we're hoping to do, and this talk should hopefully convince you as well, that we generalize this not just for single phases, but for two phases, and the way that we're going to write it, hopefully to more than two phases as well. So there's the motivation from sort of a mathematical perspective, but the motivation from a physical perspective is a little bit larger. So these top two pictures here are sort of generic stratified flows, and so there's a conservation of mass in each stratified layer. And so that ticks the box of multiple conservation laws and thus multiple phases. Okay? So in this first one, we've got internal waves. So that suggests that we should be getting nonlinear equations in there. And in fact, people have done so in the past. We've also got this sort of picturesque Kelvin-Helmholtz instability. Sort of every presentation I do has this picture. So apologies if you've seen the presentation from me before. And so this has multiple layers. You've got the stratified cloud layer, the air above it, and so you've got two fluid flows going over each other, which conserve mass, and so hopefully the theory should apply here as well. This third picture is going to be our second example at the end of the talk, where we consider models for rogue waves, and so people like Miguel Honorato and his sort of co-authors, they consider coupled nonlinear Schrödinger models to model rogue wave formation. And so if you've got coupled nonlinear Schrödinger models, you've got two conservation laws there. Unfortunately, I was going to try and find a fourth picture for Bose-Einstein condensates, but they're not very photogenic, and so I couldn't find a picture of those. Okay? So with the motivation aside, let's start the talk. So we're going to start with a general Lagrangian that will generate the system of interest. And the only thing we're going to ask that this Lagrangian have is two symmetries. So in the case of stratified flows, this is going to be two affine symmetries. For the case of the NLS, it's going to be two disjoint SO2 symmetries. Now, when we generate the Lagrangian, we're going to require that it be in a specific form. So we're going to use Legendre transformations to get rid of non-linearities in the derivatives, so that we're just linear in time derivatives and space derivatives, and everything else is just contained in this Hamiltonian over here.
Daniel, I have a question.
Yeah?
It's in 2.1, the derivatives that you have in the Lagrangian, is that shorthand for possibly allowing higher order derivatives as well or not?
Yeah, you can have higher order derivatives in there. So, for example, in hydroelastic waves, you'd have this being a function of uxx as well. And that's something I'm hopefully looking at in the future. But this is just sort of shorthand to say that the Lagrangian density depends on derivatives of the state vector as well. Unfortunately, I can't continue that forever, but that's the starting point. But those would be transformed out.
So the multisymplectic form that you have below then actually does depend on the fact that you only have first derivatives, right?
You can transform the second derivatives out as well, and so they would form part of this new state vector z. But you transform everything so that only first derivatives appear.
Sure. Okay, thank you.
That's all right. So these two matrices here, which determine the structure of the system, are going to be skew symmetric. Now, there's two benefits of doing that. One, this M and this J are going to appear directly in the conservation laws. And two, it makes the asymptotics a lot easier, because when you're considering solvability, which I'll discuss in a little while, you can just pull it through either side of the inner product just by changing the sign. So that's nice for me. It saves me a lot of work. And so that's why I put things in this form. Okay? So solutions to this equation, we're going to consider two-phase periodic traveling waves. Okay? So that means that sort of this 1 + 1 state vector Z is going to be a function of two wave variables, θ1 and θ2, which have wave numbers k1, k2, and frequencies omega1, omega2. And I'm just going to shorten it down to this. So this is a vector of k1, k2, this is a vector of omega1, omega2, and this is a vector of θ1, θ2. For periodic waves, I'm going to assume that it's just periodic 2 pi. But one of the examples I'm going to consider later is going to be related to an affine symmetry, and so it's not going to be periodic. But all that means is that I'm changing the inner product that I consider. Okay? So if I have a solution of this form, then it generates the PDE of this form for the basic state. We're going to see this guy a couple of times during the asymptotics, so it's worth pointing out that Z hat satisfies this equation. Okay? Now, in the past, systems like this have been considered by Ablowitz and Benney for the nonlinear wave equation. In 1970, I've got written down. And the problem that they faced was because they were considering weakly nonlinear solutions, they found small divisors. And so their solution, Z hat, wouldn't exist for all values of the parameters, which could be fairly problematic for us. However, Tom and his PhD student at the time, Fiona, they did a paper in 2001 where they showed that if your Lagrangian's got symmetry groups, then your solution is smooth for all your parameters. And so it exists for any choice of θ, k, and omega. It might not be physical for all of those, but it exists for all of those. Okay? And so we're going to assume we're in that case, so that our solution doesn't blow up. So now I'm going to discuss the conservation laws. So for this system with two symmetries, you can generate two vectors, the wave action vector and the wave action flux vector, which are defined by this vector with two elements. Now this double bracket denotes an inner product, depends on the problem. So for periodic waves, that's going to be averaging over each phase. For the affine symmetry, it's just the standard L2 inner product. And as I mentioned before, these inner products for each component have this M and this J. So we're seeing the structure of the Euler-Lagrange equations appear in the conservation laws. And these come together to form this conservation law here, AT plus BX equals 0. Okay? So we've got two. Now, the objects we're interested in is these two components evaluated along our periodic traveling wave, or as we'll see later, a relative equilibrium. And this turns them just from being functions of Z to functions of K and omega. Okay? So we're already encroaching back on the single phase territory. We have these functions of K and omega. So we're expecting derivatives of these, in this case it's going to be directional derivatives, to start forming the coefficients of the emerging PDEs. So we'll see them first in the linear Whitham system, and then they'll appear when we find the KdV and when we're finding the two-way Boussinesq. Okay? And so the tensors of these are important. Okay? So now that we've done the conservation laws, the last thing we need to do is start talking about how dispersion is generated. And to do that, it's ideal to introduce this linear operator here, which is just your standard linearization about Z hat. Okay? So this is also going to appear in the asymptotics, but primarily I'm using it to show how dispersion is generated. Okay? So if you take the equation that Z hat satisfies, and you take its theta, its k, and its omega derivative, you end up with these three relations here. And so they allow me to point out that this first equation, the kernel has two elements, the kernel of L, that is. And so I'm going to assume it's no larger than that, just to make my life nice and simple. And so that I can say solvability of the asymptotics later only requires the theta derivative inner produced with whatever is on the right-hand side is 0. Okay? This second equation is meaningful to me because it shows that there's a Jordan chain emerging. And so in the single-phase case, the Jordan chain was directly related to dispersion. And so we're expecting it to be the same here. And in fact, that is the case. Okay? This third one just is here because I'm going to discuss some simplifications in the asymptotics using these. Okay? And in fact, further derivatives of these equations here allow you to simplify the asymptotics later based on the modulation approach. Okay? So I guess I should talk about the Jordan chain since I've mentioned it so much. And that's what these next two slides are going to do. Okay? So 32.3a and 2.3b generate two Jordan chains of length 2. Okay? For the 0 eigenvalue of L. Okay? So if I want higher dispersion than just first order dispersion, I need these chains to be longer. Okay? Now, trivially, I could say, well, I could have this chain extend to 4 elements and this chain stay at 2, but that's not really that general. And in fact, the most general way of doing it is to consider a linear combination of the two. Okay? So we add the amount of this together, and then we check solvability to see if we have another element that satisfies this. And so by taking that inner product, we end up with this matrix system here. Now, if we go back 2 slides, if we take the k derivative of this system, evaluate it on z hat, then we get precisely this. Okay? And so we require that the Jacobian of B with respect to k has at least 1 0 eigenvalue. And in fact, we're only going to assume it has 1, because it gets a bit more complicated if it has more. Okay? And so for the rest of this talk, zeta here is going to be the 0 eigenvector of B whenever B has a 0 eigenvalue. Okay? Now, because L is self-adjoint, the multiplicity of its 0 eigenvalue is even, and so that corresponds to the fact that all Jordan chains in this setting are even. And so if I show that psi 5 exists, then I get psi 6 for 3. Sorry. Okay? So summarizing that, I end up with a sort of chain, in inverted commas, of length 4 by combining these two Jordan chain structures here into another part of the chain. And this is how it's going to appear in the theory. Okay? It can be written as a 4x2 Jordan block in a more traditional way if you consider the linear combination of the kernel elements. So if I add zeta 1 lots of this, and zeta 2 lots of that, then that would form my new kernel element, and that'd be the chain that leads to a length 4 chain. And if I consider their difference, that would lead to a chain of length 2. But I'm not going to do that. Okay? What's important from this Jordan chain analysis is the termination constant. So I'm going to assume this chain ends at length 4, and that means that these inner products don't vanish, or at least one of them doesn't. Okay? And that means that I end up with third order dispersion in my models. So that'll be third order in the KDV, like the single phase case. I guess it's technically fourth order in the two-way Boussinesq, but it will have the same coefficient as this. So we'll be seeing this pop out of the theory. Okay? So that's pretty much all the abstract setup out the way. So I'm going to move on to the actual asymptotics now. Okay? So rather than just consider a simple asymptotic sequence as traditionally is done as asymptotics, I'm going to consider a modulation ansatz. So I'm going to take the sort of independent variables, I'm treating theta, k, and omega as independent, and I'm going to add some slowly varying quantities to it, this phi, this q, and this omega here. And there's also this remainder term w, just because certain terms are going to need to be picked up by this remainder. Okay? Now, the benefit of doing that is that when I come to substitute this ansatz into the Euler-Lagrange equation, and Taylor expand about the epsilon equals 0 state, I'm going to end up with theta, k, and omega derivatives of z hat. Now, a lot of those terms are going to cancel based on these linear operator relations that I mentioned here, and sort of further derivatives of these. Okay? But this phi, this q, and this omega here are all related by what's called a phase consistency condition. Because theta x equals k and theta t equals omega, then it must be true that phi x equals q, phi t equals omega. And then I end up with this cross relation here as well. Okay? So, as I mentioned a few seconds ago, the strategy is to take this ansatz here. I'm going to put it into the Euler-Lagrange equations from an earlier slide. I'm going to Taylor expand about the epsilon equals 0 state, and then I'm just going to solve at each power of epsilon like I would with normal asymptotics. Okay? And doing that, I'm eventually going to end up with a PDE, linear or nonlinear, depending on whether certain conditions are met. Okay? Now I'm doing this for a general Lagrangian, so I only need to do these asymptotics once, and any Lagrangian that can be put in multisymplectic form, this applies to, as long as all the conditions are met. Okay? And the other reason is that the coefficients of the emergent equations are all going to be related to projections of the conservation laws. Okay? And so I can compute them in advance. The only term that doesn't do that is the dispersion, but I can also compute that in advance using a linear analysis. Okay? So the first equation that I'm going to derive, arguably the simplest, is the linear Whitham system. So the ansatz is going to look like this for scalings here. So x and t are on the same footing. Alpha equals 0 from the previous slide. Because it's linear, I'm happy to ignore phi's contribution, since q and omega are going to be the important ones. Okay, so we only have three orders of asymptotics to deal with. Okay, now the first one's satisfied because that's the definition of z hat, right? So that's done. The next one's going to be satisfied because of the linear operator results I mentioned earlier. So these two are going to cancel, and these two are going to cancel. So order epsilon 1's fine. And this highlights why we choose the modulation ansatz. Okay. The terms that give us stuff that we want to analyze happen at order epsilon 2. That's a typo. That should be a 2. Okay. And so I want to check solvability of this system. So I take the inner product with the theta derivatives, and using the definition of the conservation laws and their derivatives, I end up with this linear Whitham system down here. Okay, so these are evaluated as the k and omega up here. These are fairly arbitrary now. Okay, so the full linear Whitham system, I need to include the cross derivative as well. Okay, now Ablowitz and Benney got this for the nonlinear wave equation, but this generalizes it for any Lagrangian with a symmetry. So we've moved things forward at this stage anyway, and we're hoping to push even more boundaries by deriving nonlinear equations. So to discuss when the nonlinear equations are relevant, we need to discuss this matrix here, W. Okay, so it turns out the zero eigenvalues of W and their multiplicity determine the nonlinear equation you're going to get, which is very much the case in the single phase case as well. So the first possible case we can have is just a simple zero eigenvalue. And that actually corresponds to the Jacobian of B with respect to K having a zero eigenvalue. And so we've seen that case before in the Jordan chain analysis. So we can see that the KdV is going to come into play then. That's the first such case of a nonlinear phase equation coming out. The other case is a double zero eigenvalue, but we're only going to consider the non-semi-simple case. So that means that this matrix here is only going to have one eigenvector, and we're going to get a generalized eigenvector of W popping out as, since this is the case, and that's actually going to lead to the two-way Boussinesq. Okay, this is going to be a bit clearer when we discuss it in detail for each equation. Okay, so the first one I'm going to discuss, it's a simple zero. So as I mentioned, we require a zero eigenvalue of this matrix, and so that means we're going to have a zero eigenvector. That's kind of obvious. but that means that W has a zero eigenvector as well of this form. Okay. The consequence of that, so if I go back to the Whitham system, if this guy has a zero eigenvector, then that means that Q has to start taking a particular form. Okay. And so each function in Q isn't going to be independent anymore. They must be related by some constants of proportionality and this slowly varying scalar function U. Okay? So it's no longer just an independent vector, it's a single scalar function that has a direction. Okay? So how does the modulation change? Well, my scalings change a little bit. I've got an epsilon here, an epsilon squared here, and I've got an epsilon 4 over here because of the time scaling. Now, anyone who's done KdV asymptotics before, this is KdV scaling. That's how we chose it. It's also going to be convenient for us to expand W as a simple asymptotic series, just because then we pick up all the terms at the right time. Okay. So how do the asymptotics look in this case? So if we put this ansatz into the full equation and we Taylor expand, the first three orders just disappear, pretty much. We reobtain the definition of z hat. The fact that the theta derivatives of z hat are kernel elements means that the order epsilon 1 terms vanish, and the fact that q equals phi x cause all the terms at epsilon squared to vanish. Epsilon cubed, we end up with this system. Now this is almost the Jordan chain system that we were considering. And that would be the case if qi was equal to zeta iu. And that's what we're going to be imposing. So if we check solvability, we end up with this system. Okay. And since we were saying that q equals u zeta, this is met. So this system is solvable, and so we can write w naught as this. Okay. Now the reason I'm introducing some kernel elements here is that when we get down to the final vector system, if we don't have the alphas, then we've got two separate KdVs satisfied by the same u with different coefficients. And so the u would have to be trivial. So the alpha here is just to make sure that we're not ending up with sort of a trivial solution at the end. Okay? So the last two orders of the asymptotics we're going to consider. The first one generates this system. This comes from the fact that the Jordan chain is even, automatically solvable. We end up with some garbage terms, but they're just here because they're here. They contribute to some terms at order epsilon 5. Now, I'm not going to write down the order epsilon 5 terms because there are far too many. They are in the paper that we submitted at the end of last year. So if you want to see how scary they look, I'd say go there, but I wouldn't recommend it. But the important thing is that solvability leads to this system, okay? So this is reminiscent of the first slide, okay? We've got a k derivative of A, an omega derivative of B, we've got a double k derivative of B over here, which is very analogous to the single phase case. Again, we've got some vector k multiplying the third order dispersion. So this is looking very much like the single phase case. The only thing that changes is this guy, this new inhomogeneity, okay? So it stops it from being a truly vector KdV. Obviously, we want a scalar KdV. So to get rid of him, we project using zeta. And the fact that this matrix is symmetric means that it's also a left eigenvector. Okay? And so we end up with this KdV here, with coefficients related to the conservation laws, which is what we wanted. And we got a dispersion term, which is related to a linear analysis, which is, again, what we wanted. So I guess this is happily ever after from our perspective. Okay? So we recovered the single phase results, just generalized to two phases. Where the story changes slightly is when we have a double zero eigenvalue, which is non-semi-simple. Okay?
Before you go on, can I ask some questions about what just happened?
Yeah.
So if you go back to where you have the different scaling of the different variables, right?
Yeah.
So the fact that you have epsilon and epsilon cubed for x and t, fine. The fact that you have epsilon, epsilon squared, and epsilon to the 4, and so on for the ones above that, is there some hindsight in all the different powers of epsilon involved in terms of, I mean, if you were starting from scratch, and this is not a well-prepared talk, if you're actually doing the calculation, do you start with powers of epsilon, and then you figure out which power of epsilons are required to lead to a consistent perturbation problem?
So the way that we choose the scalings between phi, q, and omega here are so between phi, q, and omega, that's based on these two conditions here, okay? So the only way that we can get these two to balance at an order of epsilon is if they follow this structure here, okay? Because if I differentiate this with respect to capital time, I'm going to pick up an epsilon alpha plus beta. So that must be the same as the scaling on omega over here. And the same is true for if I take the x derivative of this, because I've chosen the scaling on capital X to be epsilon,
right,
then I need this power here to be alpha plus 1. What chooses alpha, though, is that's the bit that requires a bit of foresight. So I know I want to end up with KdV, so I need to think about the balance between the nonlinearity and the linear terms,
right,
and that turns out to be power 1, okay?
Okay, so there's a little bit of hindsight involved there.
Yeah, there's only at one stage, but the rest is kind of determined by the fact that you need this phase consistency condition to balance.
Right.
Yeah, hopefully that makes sense.
So on the next slide, or the next one. Yeah, so right there in 4.5 and I guess also in 4.6. So then you already know that the coefficient of u sub t is non-singular, or?
It could potentially be singular, and that's what we're going to be covering in the next set of asymptotics.
Okay.
Because that could just vanish.
Okay.
Turns out to be the case when we're considering the double zero eigenvalue.
Okay, thank you.
Okay. That's all right. Okay, so we have a double zero non-semi-simple precisely when this system is solvable, and you can show that directly from W as well, because it means that not only do we have this first eigenvector, but we also have this generalized eigenvector as well. And so for that to be solvable, so if we take the left product with zeta, that's precisely when this time term vanishes, okay? And that's kind of what you expect to be the case to lead to the Boussinesq, okay? So to modulate in that case, we could use this ansatz. So the only thing that's changed here is the power over here, because the time scaling's changed from epsilon cubed to epsilon t. However, that means you're going to end up with so many terms in this W. When I was first doing this, I kind of lost faith a little bit. So what I did was I came up with the idea that instead of just having one set of modulation functions, you introduce a second set, this var phi, it's V with gamma, and that's with some foresight, and this capital gamma over here. Okay? So they satisfy their own phase consistency conditions as well. And the reason that I do this is because then terms that would appear in W, some of them vanish because of the derivatives of the basic state, which makes my life easier, it makes the reader's life easier, and overall everyone is happy. But I'm not going to give full details of the asymptotics. Just know that this is what I'm going to end up plugging in to the Euler-Lagrange equations, and then we're going to end up with a two-way Boussinesq. Okay? So if you look at the asymptotics, orders 0 through orders epsilon 3, they're almost identical to the KdV analysis. So the only way that they change is that you'd end up with sort of a theta derivative times this var phi, and then you'd also end up with a sort of term that basically uses this. Okay, that's the only thing that changes. Everything else is the same as the KdV analysis. But at epsilon to the 4, you end up with these sort of classical terms again. These appeared in the KdV analysis, but you'll also end up with this. So the time terms brought forward one order because of the scaling in T. And so if you consider solvability of this, you end up with this system again. Okay? So that imposes as well that du dt is the same as dv dx. And then we precisely have this system here again. And we're assuming that's satisfied for the gamma. Okay? And then that means that W1 is solvable. You get a ton of terms in that. I'm not going to write them down. Instead, the important thing is that solvability at order epsilon 5 gives you this system here. So you recover these guys again, this double derivative with respect to k of b, the same k as before, but the time term changes slightly. So you're getting gamma appear in the time term, but you're also getting the omega derivative of a. Okay? So we're going to project again, because we don't want this alpha, because at the moment it gives us an inhomogeneous equation, and so we end up with a two-way Boussinesq now. Okay? Two of the coefficients are pretty much identical. The halves here because I've got u squared, not ux, and I've got this double time derivative now. That's appeared because once I projected, I took dx to write everything in terms of u. Okay? Now this differs from the single phase case because a term like this wouldn't appear when you've only got one phase. Okay? And that's the novel thing that the two phases are bringing in. Okay? So now that we've derived the equations, it could be all well and good that I've done the asymptotics, but do they appear anywhere? So I'm going to give two examples. The first one, I think a lot of people are familiar with, is two-layered stratified flow, and it's satisfied by these equations. So you've got your mass conservation in each layer, you've got your height and your sort of flux, and these will be the conservation laws we talk about next slide. You've also got these two Bernoulli equations here. Okay? So each of the psi of velocity potentials for each layer, you've got the ones appear in here, the twos appear in this layer. Thickness of each layer, you've got eta being the first one and chi being the second. The density in each layer is rho 1, rho 2. This u1 and this u2 are merely just the x derivatives of psi 1 psi 2. Okay? The only other thing that I haven't mentioned on this slide is these dispersive coefficients here. Now, these are taken from a PhD thesis by a guy named Donaldson, who was Tom's old PhD student. It took a lot of work for him to derive those, so I'm not going to write those out or try and derive them. The only thing that I need is that A12 equals A21 for this to be a Lagrangian system. Okay? Now, because there's mass conservation, there's an affine symmetry at play here, and so that means that I can write each velocity potential as the wave variable, so kx plus omega t, with the suitable subscripts. And if you put that into the Bernoulli equations, that gives you each of the basic thicknesses as a function of k and omega. Okay? Now, what I'm going to do is I'm going to reduce this system and its sort of constant velocity solutions down to both kdv and work out what condition I need for that to be true, and then the two-way Boussinesq and what condition I need to satisfy for the two-way Boussinesq to be valid. Okay? So first of all, I'm going to do kdv. So these are the conservation laws, the ones related to mass, evaluated along the basic state. Okay? So you've got your heights and your fluxes, and so if you take the Jacobian with respect to k of this and do some algebra, you end up with this condition here. So these two f's here are the Froude numbers in each layer. So that's obtained by squaring the velocity and dividing by g the thickness of each layer. Okay? I've introduced this density ratio here, rho 2 over rho 1. I'm going to assume it's less than 1 so that I'm not sort of at the mercy of the Taylor instability. Okay? Okay? So the fact that our theory has given this condition and the fact that it matches with the literature is good. That's quite a good litmus test. So there's this paper by Lawrence, I think, from the 80s, someone can correct me if I'm wrong, where he derives all the characteristic velocities for two-layer flow, and this is the first characteristic velocity. It turns out that the change of sign in this condition as well, so if I subtract the r and consider the case when it's less than 0, that signifies a change in stability and the presence of hydraulic jumps in Benton. Okay? So if I then go away and compute the relevant coefficients for the KdV based on the theory that we've presented so far, I end up with a KdV that looks like this. Okay? Now, what's really nice is that this matches the literature, albeit this is up to a scaling factor because I can scale u how I want. Okay? And that depends on how I choose zeta. But these two coefficients match the literature and some previous work that Tom and I did using a different method. So that's quite nice. This coefficient here matches the second characteristic velocity in Lorentz. So that's another box ticked. Okay. So we're going to consider now the case where this term vanishes. So that means that W has a double non-semi-simple eigenvalue. Okay? So we've got to consider the case that it might not be satisfied at the same time, but it turns out not to be the case. Okay? So let's describe the images you're seeing here. So this green surface here is this condition here, mapped out in the K1, K2, and R plane. And that's chosen for fixed eta naught and chi naught. Okay? And this orange surface here is the time coefficient of the KdV. It's R independent, so it's sort of just a nice straight plane in R. And so what's more telling is if I look at it from above, you see this black line where the two surfaces intersect. And so I have a continuum on which the two-way Boussinesq is valid, which is a lot better than the single-phase case, where you'd end up with just finitely many points. So the two-way Boussinesq is pretty pervasive. One thing to point out is that along this line, K1 and K2 have to be of opposite signs. Okay. Now that means we're in Kelvin-Helmholtz instability territory, because the fact that the two velocities are of opposite sign means that Kelvin and Helmholtz is unstable. Okay. So the two-way Boussinesq that pops out in this case, the only thing that really changes here is this coefficient. Okay. These two are the same with a factor of half here. Okay. Now this again matches the literature, both the previous analysis that Tom and I did, and also Lorentz's third characteristic, velocity. So we're pretty convinced that's right, and that's quite nice. Okay. So how do the presence of these two equations, KdV and this two-way Boussinesq, affect the flow? So what you would do is you'd solve these equations and then use the sort of modulation ansatz to plug everything back in. And so that's what I'm picturing here. So replace K plus K by K plus Z to U with a relevant scalar. Okay? And what we're seeing here is the internal interface, this eta naught, and this top interface. And what I've basically done is I've chosen U to just be set squared, and then used the zeta that you'd get in each case to determine how this is going to change the surfaces. Okay? So in the case, we're getting this interesting looking solitary wave in the middle, and your sort of standard Zetron at the top. And in the two-way Boussinesq case, you're getting something more interesting at the top and something standard in the middle. Okay? And this is just to show you that by solving these equations, you can end up with sort of physical intuition for what's going on. Okay? So that's the first example dealt with. The second example, as I mentioned at the beginning, is related to rogue waves and a little bit to Bose-Einstein condensation as well. So some people have considered this model for mixing of two condensates. But what I'm more interested in is the freak waves. So that's considered by Vosk back in the 70s. And more recently, I think I've got written down 2006. Yep, 2006 by Onorato and his collaborators. So they looked at sort of plane waves in this and had a look at modulation or instability to see when that's going to be relevant. Okay. So the periodic waves I'm considering here are just your simple sort of complex exponentials for complex amplitudes A0 and B0. Okay. And they satisfy this equation here. And they're associated with this SO2 symmetry in each of the variables. Okay. So let's discuss the criticalities and when the KdV and the Boussinesq are going to be relevant. So the conservation laws here are the mass and the mass flux again in terms of the amplitudes. And so if you take the Jacobian of B with respect to K, you end up with this surface here in K1, K2. Okay. Now this is a lot more diverse than the shallow water case because you've got more parameters to play with, and so you're more likely to achieve criticality. So the KdV we're going to get here more likely to get. Okay? And this is the KdV equation you're going to get as well. So when we come to discuss the two-way Boussinesq, this is the one we're going to have a look at. We're going to see when this guy vanishes. But before I do that, I'm going to have a look at how solutions to the KdV affect the wave trains on the previous slide. So let's describe the pictures. This first one is A, with everything chucked back in, and B with everything chucked back in, where the everything that I'm alluding to is just a solitary wave sec squared. Okay? So we're getting a bright solitary wave, we're getting a dark solitary wave, and what's interesting is, for example, in Honorato et al., where you've got these two wave groups interacting, so we want the sum of them. You're getting this rogue-like event at the origin, okay? Because you're essentially tripling the amplitude. And so the fact that KdV appears here is actually alluding to solitary waves at this Jacobian vanishing, okay? And we've got some parameter values down here, which will make more sense on the next slide, okay? And you can do these simulations for various parameters as long as they lie on that surface, okay? So in the double zero eigenvalue case, we can find one example of criticality. There's plenty more, but this is one of the simplest. I'm going to choose that omega 1 and omega 2 are the same, but they have to be negative because of this. I'm going to choose alpha to run between -1 and 0, just because those are the values that Salmon and Berloff choose, because they also set beta to be negative unity. Similar to the stratified fluid case, to reach criticality in this case, I need K1 and K2 to be of opposite sign. Okay? And along this curve, we're getting a continuum of solutions as well. So it's a pretty pervasive equation. But there are more examples where you can get the two-way Boussinesq, but this is just the simplest one that I could find. Unfortunately, I was going to put some surface plots in here as well, but they look pretty messy. They made my head hurt. They'll probably make your head hurt too, so they will be saved for another day. Okay. The two-way Boussinesq in this case looks a lot nicer than the previous equations that we've seen. We got sort of very short expressions for the dispersion term. This is non-zero. This is also non-zero. So the only term that can vanish here, and we'll talk about why that's interesting in a little bit, is this time term here. Okay. Unfortunately, no one in the literature has looked at the characteristic wavelengths for this system that I'm aware of. If you know, do hand it over. But we can only guess that these coefficients are right. Okay. So what the solutions of the two-way Boussinesq look like when you solve them and plug them back into the waves? Now it turns out you get even roguer waves. Okay. So it turns out the bright solitary wave before becomes a dark solitary wave, and the dark one becomes a bright one. But when they're added together, you get this really stark peak now, and it really is quite rogue because you're going from 3 to 9, and so we're really saying that these reductions are giving physical intuition now. And there's some parameter values down here, but you're free to simulate them for a lot of choices of omega. Sometimes the amplitudes won't be physical in those cases, but for the large majority they are. So those are the two examples. Hopefully they've looked interesting. I found them interesting. But where do we go from here? Okay. So here's a summary of most of the stuff that I've done today. So we derived this. We showed that when you end up with this zero eigenvalue condition, you're expecting the KdV equation. Now, if you've got a double zero, you expect two-way Boussinesq. But this by no means is the only set of coefficients that can vanish. So, for example, you may find that this guy disappears, and so you expect higher nonlinearities. It can be the case in sort of stratified shallow water, that's what I've been looking at recently, that this guy vanishes as well. And if so, the asymptotics leads to a fifth order KEDV. Okay? Well, what I will be talking about on the next slide in particular, just as a kind of ad hoc guess, is when the time term in the two-way Boussinesq vanishes, you actually end up with a third order time derivative in your PDE, which looks kind of scary, but it could be quite interesting. The other case I would just want to flag up as well, we've been considering the simple zero of DKV, but what happens if it has more than one eigenvector, and so like double zeros? In that case, you'd end up with multiple projections of, so if I go back quite a few slides, so here we were just projecting with one eigenvector. But if you end up with more than one eigenvector, you project more than one. So you end up with a set of, for example, Boussinesq equations or a set of KDV equations. And people like Grimshaw have seen this before, but haven't been done in the modulation framework. So that's in red because I haven't quite done it yet. I'm hoping to do that sometime soon. So let's talk about sort of these three guys here. So if you end up with a triple zero of this matrix W I introduced a lot earlier, then the time term in the two-way Boussinesq vanishes, and so if you redo the asymptotics with appropriate scalings, you introduce even more modulational functions, so there's a lot to keep track of. You end up with an equation that looks like this. Now, I have no idea what it does. It's just, it pops out. But it requires this additional eigenvector here to pop out. Okay, that's all I know about it. I haven't studied it. I tried to find it in the stratified flow, but it turns out the time term there for the two-way Boussinesq is pretty robust, so I can't get it to vanish. But in the NLS example, that changes sign. And so there will be cases where the coupled NLS gives you this equation. And I want to look into that a bit more. There are other places, like I mentioned before, like where this guy and this guy vanish. And so you'd expect high dispersion when you can solve this system, and higher nonlinearities when you can solve this system. But these conditions aren't related to W. Every other condition we've discussed today has been related to W, but these ones start breaking that mold. Okay? The other things that we can do in this framework, we've only done this for one space dimension and one time dimension. You can get KP as a sketch calculation if you include another space dimension, so you include another conservation law, and so you get more coefficients related to the conservation laws. If you have a double zero of the W again, you end up with the two-way Boussinesq, so on and so forth. You just end up with the 2+1 analogies of the equations we've seen here today. One thing that I won't be doing, but is probably worthwhile someone doing, is the validity of these reductions. So it's something we haven't even done for the single phase case, and we're hoping someone gets interested in doing, because it's all well and good doing these reductions, but they could diverge from the original solution, or solutions of the full system, quite sharply. So we've only done half the story, really. What Tom's been doing recently in the single phase case is considering modulation close to Lighthill points. And so what that means is that instead of two conditions for the two-way Boussinesq to come out, you only need one. Now, extending that to multiple phases is not obvious at all. I don't know how to do it, but I'm hoping to look into it soon. And the last one is, we've considered Lagrangian densities, but there are systems that have spatial conservation laws, like Swift-Holmberg, Ginsburg-Landau, and they're generated by functionals, and so they're gradient systems. The theory here is probably going to apply to those. And so we can generate the parabolic equivalents of the KDV and the two-way Boussinesq in the form of the Kuramoto-Shifushinsky equation and other higher-order PDEs. And so I think that's all I want to say today. So that's all you're going to hear from me. If you've got any questions, feel free to ask. But thank you for listening. Okay. Okay, so
Questions?
That's my question.
No. Well, if there's no questions. Okay. Well, if there's no questions, let's thank Dan again. Thank you, Dan. I hope it was okay with recording everything, and I hope you liked it.
yeah, no, that's fine. No, thank you for having me. It's been good to talk. Hopefully, I didn't confuse you too much.
Just the right amount.
That's the right amount.
Thank you.
Thanks. Bye.